In this series of videos I'm designing a Z80 based computer system. As much as possible I'm sticking to a discrete design using TTL logic devices. Just a couple of large-scale devices including the Z80 itself. And so far I've got as far as designing the core system. If you've read the book that I produced as part of this project, you'll know that it's very discrete in design, but it includes things such as direct output for driving a CRT monitor. All the timing is generated discretely and it works quite well, but I got to the point where I wanted to add a floppy drive control system. And to add that to this version, this is version 4 of the board, so it's one version newer than the book covers, but there's not a great deal of difference between the version 3 that the book shows and this version 4 board. The main differences are things such as the inclusion of a sounder, being able to control the interrupts through firmware rather than with physical jumpers. It's that sort of thing. But I'd gone as far as I could with the design. I have in the last few videos in this series shown the floppy drive control system, or at least the start of it, and that works quite well, but it's just hooked onto the design development connections at the end, which take all these signals out for the buses and control signals, so we can then use the board to design more of the system. And the next step has to be quite a big step in terms of design. We can't really do it in small steps, because what we need to add to include our floppy drive control system, bear in mind I want to include DMA in the control, is we have to add a number of circuits. Firstly, the floppy drive interface that you've seen already, but for the DMA we need to add a loadable 16-bit counter. We also need to add some relatively complex control for that DMA system, and also I want to make the new board compatible with the version 4 board, in as much as I want to be able to enable or disable the DMA system so that the floppy drive interface can be used using programmed in-out. So it's quite a lot to add, but I couldn't just add these circuits to the version 4 board for a number of reasons, but the main one was the buffering. So although there was some buffering in the version 3 and version 4 boards, it wasn't particularly extensive buffering, and certainly not sufficient to allow us to add many more devices. In fact, with this board, some of the Z80 types will not run properly. They'll run, but they'll be very flaky in operation. The reason being is because there's very little buffering on the data bus, and the Z80s were struggling to drive the data bus. The same was true to a certain extent with the address bus, but there was more buffering on the address bus, so it was less of an issue. So to go any further with the design, as well as adding the required circuits, I also had to completely change the board to add very extensive buffering between the Z80, the data bus and the address bus. But it's not as straightforward as it may sound, because the address bus it's not particularly complex to drive, but it does need to be able to be tri-stated if I'm going to use DMA, because obviously the address bus has to be put into tri-state mode so the DMA circuits can use it. The data bus is a bit more complex because it's a bidirectional bus, and so you need to be able to control when it's feeding data onto the bus, when it's reading data back, and again it has to be tri-statable so that the DMA system will work. What I ended up designing was splitting the data bus into 3 separate buffered data buses, and they can all be controlled independently. And the reason I went for 3 buses is so I didn't end up with another fan-out issue as we add more devices. And that means that the design from this board to the next board is quite a big step, because it completely changes the way that the Z80 is connected to the rest of the circuit. Most of the circuit can be kept the same, but the buffering of course changes things quite a bit, and if I make a mistake in the way it's controlled, the new board won't work. That is of course going to require quite a big change to this layout and this board. So I've designed the board, designed the circuits, I ordered the boards, and they finally turned up. Now as you can see, it's a much bigger board than the version 4 because there's a lot more on it. We've got all the buffering, which you can see down here. We've got the Z80, the ROM, clock and clock divider, and then this column of ICs are buffers that effectively buffer the Z80 from the rest of the system. And then at the bottom here I've added the DMA counter, and on the right bottom corner we've got the floppy drive interface. The rest of the board, the layout's completely changed. If you do build any of these, if you get these boards and you build them and you decide to go from the version 4 to the version 5, then just be warned, the layout's completely different, so you can't just take this IC from this location and put it here, because the entire board layout's changed to make the layout more suitable for the new design. Now the version 5 board, which is this one, is also a 4-layer board, and I've gone down that route because I have the option of either making the board even bigger to allow decent power traces. This power requirements on this board is obviously a lot higher than the version 4. Or if I went for a 4-layer board, I could keep the board relatively compact and use a ground plane and power plane, which is what the two internal layers are. So there are no traces as such on the internal layers. We've still got the X and Y traces on the top and bottom layer, but the internal layers are ground and power planes. So the next thing I have to do is get one of these built up. So I'll get one put together, I'll populate it. Normally I would go through a very comprehensive step-by-step test procedure with a new board, but because a lot of this has been tested already, albeit it's a new layout, and if I've made any mistakes it's of course not going to work, but the circuits themselves, if they are correct, should work relatively reliably. But of course this is a completely new design in terms of the buffering. But rather than go through it step by step, what I'm going to do is build up a board, put most of the ICs in it, and then we'll power it up. I was going to do this kind of off camera and show you the result, but I thought you might be interested in seeing the first power up of the new board. So I'll go and get one assembled, and shouldn't take too long, come back and we'll see what it actually does. Okay, I have the board made up. I have not really tried powering this up yet. All I've done so far is put all the passive components on and the sockets. I did power it up and test for shorts without any components fitted, without any ICs fitted. I then fitted the clock IC, which is this one here, powered it up with no other ICs fitted, checked for the clock, and that was working fine. I then fitted the divider, powered it up, and that was working fine. So that's the only testing I've so far done. So we are getting a clock, and it is getting through to the correct pin on the Z80 socket. So that's the only testing I've done so far. I thought you'd be interested in seeing the first power up, so I thought I would video it. And also, if anything bad happens, it will give me a video record as to what may have gone wrong. So it is quite useful videoing these projects sometimes. It can give me some good information. I haven't fitted all the components yet. I don't have the floppy drive interface connector fitted. I haven't fitted the floppy drive interface ICs. I have fitted the DMA counter ICs because some of them are used for other things as well. So I fitted all the devices that should allow the system to run. I've got the same ROM as ROM contents as we ran on the version 4 board, because that should still work on this board as well. And I haven't got the monitor fitted, as you can see. I'm not sure we'll get that far, but what we're going to do here is power this up and see if it is capable of running at all. Like I said, this is a huge step from the version 4, so anything could happen. But I do have all enough components fitted for the system to, in theory, start up and give us some video out. Now, because we don't have the monitor fitted, I've got the scope on standby, and we should be able to probe the output pin of the video connector, which is this one here, to see if there is any activity on the video output. We should be able to kind of gather whether it's running to a certain extent or not, and whether the video output looks correct, and we'll kind of explain this as we go through the process, assuming it will run at all. I've got the keyboard plugged in as well, and I've got all the components in for the PS2 interface, so in theory it should be able to read the keyboard. And what I expect to happen when we power this up is the sounder should come on for about half a second. Now if it comes on and stays on, it means the board is dead and it's not running at all. One of the first actions of the Z80 boot up code is to turn the sounder off. So if it does go off, if it comes on and then turns off, we can be fairly confident that the system is fetching instructions and seeing them correctly, and also that it's able to talk through the buffers to turn the sounder off, because bearing in mind it has to have bidirectional control of the buffer, because the ROM and the RAM are now outside the buffer, whereas previously on the version 4 board they were inside the buffering, so there was no issues with regard to controlling the bidirectional buffer. But of course that buffer now needs, at least the one on the data bus, now needs to be able to switch from read to write mode depending on what the system is doing. So it's quite a complex change. And also the circuit that drives the sounder is on a different data bus, so that buffering needs to work as well. So it's quite a lot within the first half second that will give us a clue as to whether we are on the right track here. Now what should also happen, we should see the power LED come on. I haven't got all the LEDs fitted yet, I'll come back to those in a future video. The power LED should of course come on, and then I've got this LED over here just poked into the board, it's not soldered in. And that should come on when we power up the board. Again, assuming that the Z80 can talk to the port. It's actually connected to one of the pins on one of the output ports. And this ROM contains the cell test that I described in an earlier video. So it tests the checksum for the ROM, it checks the SRAM, checks the bank 1 RAM, checks bank 0 RAM, does quite a lot of checking. Got all the DRAM devices fitted of course. Now when it's running the cell test, this LED comes on, and so what's going to happen, it should come on, cell test takes about 5 seconds. We're running the Z80 at 2.5 megahertz, so it's quite slow. But then what should happen is the LED should turn off. If any of the self-tests fail, assuming that the Z80 is capable of running at all, then the status LED, this LED, should flash a code to indicate which of these self-tests failed. But ideally what should happen, we should power up, a brief beep, this LED should come on, stay on for 5 seconds and then go off. Like I said, it's such a big change in the design that that is not necessarily what's going to happen. So we'll give it a go. This is the first real power up for this, so fingers crossed, let's see what happens. I've got the power supply set at 5.1 volts and it's set to a current limit of 1.2 amps, but the voltage drop across this board should be quite minimal because it's, as I say, it's got a ground plane and power plane, so we don't have the drops in the tracks that we would have on the version 4 board. So without further delay, we'll turn this on. Fingers crossed, we don't want to see any magic smoke escaping, and we want a brief beep, 5 seconds from the status LED, and let's see what happens. That's promising so far. The LED is on. Let's see if it goes out. Now it's gone out. We're drawing 1.2 amps, just under 1.2 amps, which is exactly what was expected, and this has gone out. Now what we can also do at this point is use the scope to see if we're getting anything out of the video. So we should have 3 signals coming out. We should have a fairly slow one, which is this one, 48.3 Hertz. That's obviously our field rate, refresh rate, so that's perfect. That's just what it should be. One at about 17 kilohertz. is our line, and that's 17.8 kilohertz. Again, that's perfect. And then we should have some video output. Let's see if we're getting anything, and we are. So if we had the monitor attached, what we should be seeing on the screen is the JNZ startup logo. Now, of course, if the PS2 interface is working, if I press a key on the keyboard, this should change. Bear in mind, this is the first time I've run the board, so I don't know if this is actually going to work. So I'm going to press a key. It has indeed changed. That's looking quite promising. What I can now do, I'm not blocking the camera here, is I can press the T key on the keyboard, because in theory what should be on the screen now if we had the monitor fitted is the menu for the monitor, and the T option should run the self-test. So what we should see on the screen is a lot more activity, because it fills the SRAM that supplies data to the video with a character which will fill everything, so the entire scope display should be continuous data. But also the LED should come back on because we're running a self-test. So let's try this, fingers crossed. And it's gone out, and we're left with just the message on the screen. So if this was the video, the CRT, this is just the text saying that the monitor is available. But as a first power up, it's looking very promising indeed. I don't know if any of the rest of the circuits work, but it is looking like the system can at least run. The buffering appears to be working as it should, because all the things we looked at so far are on 3 separate data buses. And for them to work, they all have to work correctly, of course, because if they're not being properly selected, we won't get the correct data. So the video, for example, the fact it's changing at all means that the Z80 is capable of writing to the video SRAM. The fact we're seeing changing data means that there's quite a high likelihood that the video output and the way it turns the parallel data from the ROM into serial data is working as well. That's not that surprising. It's almost a self-contained circuit, but the fact that it can be changed means that the Z80 can at least access it, and it can access it through the buffering. The next steps in testing this will be to run some specific test codes, see if the RS-232 works, and then I can start investigating the rest to see if all the ports work, if all the in-out works, if the status works. Well, status word, of course. And then I can start running some more comprehensive tests. Assuming they all pass, I can then start checking to see if the DMA counter works, and if that works, I can populate the floppy drive interface devices, and we can start investigating the floppy drive itself, see if that works. We'll start in program mode using the code already in the ROM. If that works, I'll write a slightly different version of the ROM, or may just download some test code through the RS-232 if that works, and we'll write a version of the bootloader that uses DMA, and we'll start seeing if that circuit works. Pretty sure we'll encounter some issues along the way, but this is a very good first step. Okay, I've got the board connected to the monitor, got the keyboard plugged in, we're hooked up to the power supply, and this is again the first power up with the monitor connected. I thought you'd be interested in seeing it, warts and all, so you'll see what I'm seeing. Hopefully it will come up and we'll see the logo. There was something coming out of the video port as we saw earlier, but it's only when we get the CRT attached we know if all the timing's correct and it's properly synchronized and we're getting what we expect to see. In theory, the display, if it's working, should be a bit clearer than it was before because we've got much better grounding on here, but you can't really tell until you try it. So we'll get this powered up and see what happens. It'll take a few seconds for the CRT to warm up. Got the LED attached still so we can see if the self-test completes, which it has done. And we've got the startup screen which is very promising indeed. Still saying version 4 of course, because this is the ROM out of the version 4 board. But I can't see any artifacts. It's nice and clear. It's much clearer than it was on the previous board. I'm going to dim the lights a bit, see if we can cut down some of the flicker that I can see on the camera. I hope you can see that a bit more clearly. So I'll hit a key on the keyboard and we should close the startup screen and we should see the header for the monitor, which we do. No strange artifacts on there either. It's nice and stable. Press the help key and we should get the menu listing for the monitor, which we do. So it's all working, the blanking's working, the sync's working, and it is, you probably can't tell on the video, but the display is very much clearer. I had some comments by the way about this tube having severe screen burn, but unfortunately it's the only spare tube I have, so I've had to carry on using it. On the lookout for a new tube to carry on this project, but until it arrives, until I find one, we'll have to continue with this. And we should now be able to rerun the self-test, and we should see the LED come on. The screen will obviously have a lot of characters on it, as the self-test does include the video SRAM. And that's what we expect to see. That should clear in a few seconds, which it does. So very promising. We'll try dumping the RAM. In fact, we'll try dumping the ROM to start with. And that's working fine. This is running at 2.5 megahertz. What I'm going to do now is power it off, move the jumper so that we're at 5 megahertz, and see if it still runs at the highest speed. So we'll just power this off. Change the jumper setting. Power it back on. And we're certainly getting something on the screen. It looks fine. That looks fine. We'll try dumping the ROM again. You can see how much faster it is at this speed. We'll run the self-test. Should complete a lot more quickly. We'll see the LED should only stay on about half the time, which it does. So that's it for this video. You can see that the new board so far is behaving itself. I've got no idea if it will talk to the floppy disk drive. I don't know if the ports are working, but judging by how nice and stable the display is, I'm assuming that we're well on the way to getting this working. But there are so many things that can trip this up. There's literally millions of different issues that can arise when you design something like this. But hopefully we're getting closer to a final solution for this design. This is really as far as I would be taking the design. If I can get all this working, then that would probably be as far as I take the hardware design at the moment. I will add other things on, but they'll be connected to the ports. But what I really want to get working here is the floppy drive interface, the DMA, make sure all the buffering's working, and then from there I can try and get a version of CPM running on this machine, and then from there I can write my own operating system. But as you can see, making good progress.